Okay, so lecture 26, quantum electrodynamics. So review of lecture 24, 5, because I cannot count. Quantization of electromagnetism. Electromagnetism, we start by saying that the Lagrangian density is minus quarter F mu nu, F mu nu. F mu nu is the field strength, it's an observable. F0I are the electric fields, and the Fij's are related to the magnetic field. These are observables. We said that the theory has gauge invariance, meaning that if you send a mu to a mu plus del mu of alpha, in alpha any function of space-time, this alpha, there's no physics associated to it. It's just a redundancy. And I did not really describe this, but gauge theories come about because you have a theory that has non-local degrees of freedom and you insist on locality, writing a local description. It comes, you pay a cost, and the cost is ending up on physical redundancies. Never use the terminology of symmetry. Gauge symmetry is nonsense. There's no such a thing as gauge symmetry. Gauge transformations, gauge invariance. That's old and incorrect terminology. All right. A mu, what we did was that, we talked about canonical quantization, and we also talked about the covariant way of doing it, but we start with the canonical quantization. In this setup, you pick slicing the space-time into space and time. So you break Lorentz invariance, you pick a frame, you refer to the spatial part of a mu as vector potential and the time part of it as the electric potential. This J mu is the current density that is coupled to the electric field, and for current. The current density is the spatial part of it, and the charge density is the time part of it. If you just take this action, we did this much earlier in this course. If you do a variation of the Lagrangian density with respect to the dynamical field A mu, you find the equations of motion. We found it to be the Maxwell equations. These are four equations that are Maxwell equations, sourced Maxwell equations. And it's pretty obvious from the fact that F mu nu is antisymmetric that if you take a derivative with respect to nu here, this is symmetrized, this is symmetric, this is antisymmetric. So this has to be zero, which means that the current is conserved. Good. Any questions about this part? For those of you guys who are curious, you might hear this nowadays. It's more popular to talk about this terminology. Last year I explained this, but this time we didn't have time for it. Global symmetry is a zero form symmetry. Gauge invariance is something that's called one form symmetry. So I explained this last time, but this is more modern terminology. There are also higher form symmetries, blah, blah, blah. All right. Any questions? We talked about the A0 not being non-dynamical. It simply is a consequence of the fact that there's no conjugate momenta. We saw that explicitly. There's no dynamics associated with it. Therefore, we could just simply solve for it and plug it back into the Lagrangian. We used gauge invariant. We could fix the gauge, and for example, you could set A0 equal to 0. That's a particular case of a temporal gauge. You could use, you could pick an arbitrary 4 vector and contract it with a mu to equal to 0. This is axial, light cone, or temporal gauge, depending on this vector n mu when it's space-like, null, or time-like vector. Good. You have to further, there are other choices of gauge invariance. There's a Lorentz gauge and Coulomb gauge. So Coulomb gauge clearly is more appropriate for canonical quantization because it treats the spatial and the time part of the vector field separately, whereas the Lorentz gauge is more convenient for Lorentz covariant expressions. Good. We discussed last time the Coulomb gauge. The Coulomb gauge is basically a statement that you project out this part of a mu, AI, spatial part of it. The idea is that you want to set this equal to 0, and this projection does it for you. Do you recall what this condition was? What is this? What's the physics of this? It's very easy to understand. What's this in Fourier space? This is KI equal to 0, right? So it means that if you have a 3 vector AI, so this AI is a function of K, right? It cannot have an element in the, so AI has to belong to the perpendicular plane, 2D perpendicular plane to the plane of propagation. And a simple way to do that is just to project out the component that's along the propagation vector, and this is the projection that does that. All right, then what we did was that, well, after imposing the Coulomb gauge, plugging this back into the Lagrangian density, here your AI field is a dynamical field. Recall that this is just a pi squared term, right? This is a canonical conjugate. This is a kinetic term. And the Coulomb part of it is the part that we explicitly solved for. And this is just, we saw that it basically contributes to the shift of the Hamiltonian energy density at various points in space-time. So if you give me the charge configuration of charge distribution in the universe, I can simply solve for it, plug it into Lagrangian. There's no dynamics associated with it. All it does is that quantum theory shifts the vacuum energy and vacuum energy density. All right, any questions about this part? Then last time we continued by looking at the equations and trying to solve them. Well, the solution was pretty straightforward. You saw that the equations of motion basically look like three scalar field with an extra constraint that kills one of them. So you introduce A and A dagger equation annihilation operators the way that we did for free boson. Here these are massless, so the dispersion relation is simply this. This is a dispersion, and the index lambda keeps track of the two-dimensional polarizations, right, perpendicular to the direction of propagation. So it's a massless spin 1 mode, has 2 degrees of freedom. We also saw this when we went over the representation through Lorentz group, if you recall. Do you remember what the deal was over there? We were talking about the little group, and the little group for a massless particle had we described that. Okay, so here are the 2 crystal polarization vectors, but it's for a photon. That photon is this guy. Photon is one particle state of that field that propagates in the z direction, but these are conventional. You could pick different polarization. These two are called the left-handed and right-handed polarizations. You can probably guess why we talk about that. Again, if it seems kind of mysterious to you or we're wondering where it comes from, go back to the little group and you'll see where this comes from. Okay. So what are the canonical commutation relations? Of course, A lambda and A lambda prime dagger satisfy the standard commutation relations that you expect for simple harmonic oscillator. There are 2 of them. This is the dispersion. And the commutation relations of the AI and the canonical conjugate is as you expect, except that you have to make sure you project out the unphysical degree of freedom. So this is a gauge constraint. This is a gauge constraint. Polarization is always on the plane, confined to the plane, perpendicular to the direction of propagation. That's what it means. Questions? Something I explained last year is that if you have a spin 1 massive particle, then you have you no longer have this condition. So you have 3 degrees of freedom. So if photon had a teeny tiny mass, absurdly small mass, it would completely change the history of our cosmos, like from Big Bang to now, everything would change. We're not talking, it just adds the existence of an extra degree of freedom can completely change everything. So we're pretty darn sure about photon being massless. also it can be gauge theory, but you don't know that yet. All right. Actually, yeah, well, I haven't explained what gauge theory is, so. Questions? I think next year when I teach this, I'll bring the gauge theory back. We also did, towards the end of the last lecture, we did the quantization covariantly using the path intervals. We saw that, well, this is a Fourier transform of the equation of motion. And we saw that it's not invertible, right? Therefore, you have to project out the zero eigenvector and then invert it. This ends up being the propagator in the so-called Lorentz gauge, right? Good. Recall what the Lorentz gauge was. Do you remember what the Lorentz gauge was? It's del mu a mu equals 0. The Lorentz gauge is something that, because it's covariant first, and it's very, very helpful and useful. When we talk about fancier gauge theories next semester, we'll use another gauge, which is intimately tied to Lorentz gauge. But yeah. All right. So, any questions about the propagator in Lorentz gauge or Coulomb gauge? We saw all of those. You should get very comfortable with the propagator, the photon field, and these different gauges. You will see that actually, as I start doing actual calculations, I'll start playing tricks. The calculations are long. Sometimes I know a term is all going to be, you pick a gauge, you're doing a calculation, then there's a whole term. But you realize the index structure sitting outside is something that you could set to 0 with a different choice of gauge. So you stop calculating that term and move on to the next one. So in QED calculations, this is very common. You have to pay a lot of attention to the index structure and what the terms are. Some of them it's just you could simply set to 0, or it's just pure gauge. There's no physics associated with it. I'll give you examples of that. All right. So this brings me to this lecture. Any questions from what we discussed last time? So what are the interacting theories you've seen so far? Yukawa, right? What was the Lagrangian in Yukawa? So here's the scalar field, Lagrangian density. What else was there?
Wait, no, it's psi bar sine.
Right. So there is psi bar. Okay. No. Gamma mu del mu psi. So this is a fermion, Dirac fermion. You could add masses here, right? So you could add a mass here. How do you add a mass? Here's how you add a mass. So this is a free Dirac fermion and a free scalar. Now I can couple them. What was the coupling in the case of forget minus or plus? What I put here? I think minus. What was the coupling in the case of Yukawa? Psi bar psi phi some g. Right? This is basically the simplest, lowest order in derivatives and powers of the field interaction. You can write down. That's Lorentz invariant. That's consistent with the symmetries, right? Good. So this is one theory. This is Yukawa. You also know lambda phi 4. I think we talked about it. Did we? Yeah, I think we did. So there are various ways to write it down, but let's just say something like this. Now we're going to talk about another theory. Well, now you know about the free theory, which is photon theory. It's a theory of photons. You could try to couple the photon to a scalar, or you could try to couple the photon to fermions. if you couple a theory of photon to a fermion, Dirac fermion, that theory has a name. It's called QED, quantum electrodynamics, right? So here, what are you going to add? First, you have to add the kinetic term for the fermion. And then now you have to write an interaction here. What interaction can you write down? Just stay consistent with the signs. I think I'm missing. Oh, sorry. Here I wrote it correctly. There's an I here, there's an I. What is the interaction I can write down? That's Lorentz invariant. What terms can you think of? A mu, what? Psi bar, gamma mu, psi. There we go. So then put something here. This coupling, what's the dimensionality of this coupling? Well, calculate it for yourself, but this has a name in QED. What's the name of this? Electric charge. So this is the electric charge of the particle. All right. So here's what the QED action looks like. As I just said, sorry for the convention change. It keeps switching around. So I del slash minus m. This is the fermion term. This is the coupling of the photon and the fermion, and then you have the action of the fermion. So what are the Feynman diagrams look like? Well, actually, let me first tell you about. Oh, let me first tell you about the Go over the Feynman rules, and then I'll come back there. So what are the Feynman rules? Of course, you're going to have the propagator for the photon and the propagator for the fermion, right? And those are all the propagators you have. So what's the propagator for the photon? What was it? So P mu nu, right? So in the Lorentz gauge, it was this. I don't add a mass down here, right? Because there's no mass. It's massless. But you want to, I wrote Feynman propagator, so I have to put an I form, right? Okay. Now, there is another gauge called Feynman gauge, which is in Feynman gauge, figure out what Feynman gauge is. But in Feynman gauge, the propagator becomes A to mu nu over Q squared plus IS. All right. So for the incoming particles, the incoming photon, of course, is going to have e to minus I p dot x. But you also have to tell me what is the polarization of the incoming photon. For every different momentum, there could be a different polarization. So here's a vector, right? It's a 4 vector, but there are only 2 degrees of freedom in it. The outgoing photon, the polarization vector star e to IPX, but there are only 2 degrees of freedom. So this notation should already tell you that if you take any external leg, if this is an incoming and outgoing photon, so these are external legs, and you contract it with p mu, you should get 0, right? Because the polarization vector has to be perpendicular. So those kind of relations are in lines with something that are called ward identities. This is just a consequence of the fact that we have a gauge-invariant theory, right? But we'll use that a lot. Good. All right. Oh, sorry. I should have. That was bad. You have to put a mu and mu here, of course. Always. All right. So what are other propagators we have? We have the fermion propagator. It looks like this. right? Plus I epsilon, if I'm putting a F here for Feynman, I should put I epsilon here. And now there's an interaction vertex. I just erased the term in the Lagrangian, but you could easily convince yourself that the term corresponding to this interaction in Feynman diagram is minus IE gamma mu. That's the interaction term. Why is there a gamma mu there? Is it clear? Well, the diagram has a mu here because there's a photon coming in, and the other legs don't have a mu. Good. What other labels do the other legs have? They carry the spin. So I'm suppressing that. Right? So these guys carry spin. So incoming fermion, UPE to minus IPX. What is UP? It's a 2 vector. Up and down spin. Outgoing fermion, U bar P to IPX. Hopefully these you recall. Incoming antifermion, V bar P to minus IPX. Outgoing 1 VP. Right? The polarization, well, sorry, spin, not polarization. The spin is inside these U's. Questions? So these are the building blocks of Legos of QED Feynman diagrams. I'm hesitant to make this comment, but it's just last time around I explained this, but sometimes people write this. So look at the interaction term and look at the kinetic term. You could define a notion of D slash, which is this plus IE. How do you want to do it? You could define D mu as del mu plus gamma mu. No, sorry, A mu. Incorrect. A mu. Sorry. It looked wrong. This is called a covariant derivative, and it's a way of repackaging things. But because I've not explained the origin of gauge theory, at this point it's just a notation. Good. All right. So what are we gonna do today? Now you know the Feynman diagrams. First thing that we have to do is, well, let's just start doing some calculations. What are the processes that you could imagine? What kind of scatterings can you imagine? Well, you don't have any unstable particles, right? So there can't be one incoming or one outgoing things. So you have to have at least 2 things coming in. So let's just start simple. I'm gonna draw 2 incoming things and 2 outgoing things. Give me the options. What is there? What's out there? A photon, a fermion, scattering to photon. It couldn't have been anything else, right? So the mu here, if you want. Okay. But this could be anti-fermion. Right? That's the direction of this. What else is there? I could scatter fermion, 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 anti-fermion, anti-fermion, fermion, anti-fermion, all of those things. All right. Good. What else? Can I have something like this? Photon, 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 photon. Yes. All right. So let's go one by one. Let's draw the simplest Feynman diagrams that would contribute to this, the lowest order. What would it be? So I erase this, right? The lowest order. What does lowest order mean? Well, you only have one interaction, this. This carries E. I can't have only one E, one such vertex here. I need the lowest number of things I can do is order E squared. And I have 2 of them. So what do I draw here? What are the options? So this is one option. There's another diagram that contributes to this process. Yes. That's right. And how do you add those diagrams? can give you the answer. Do you add them or do you subtract? Yeah, they're anti-Semitic. They're outgoing legs of fermions, so you have to subtract them, right? Pauli's exclusion principle. So here you're doing this minus this. So we're going to do that calculation. I think it's right here. But before doing that, let's talk about this guy. So what can I do here? What can I draw? Similar. Like, what does that mean? Tell me what to draw.
So this should be fermion.
So fermion comes out of this. Yeah. I can draw them, but first of all, where do you attach this? Do you attach? Can you attach? Are you going to attach these ones or not? No, we're not going to attach them. Okay, then what are you going to attach here? Two fermions. Okay, like this. Then what are you going to do? Are you going to attach these two?
Yes, and then bring out the photon.
Okay, then this comes here. What happens here?
It attaches to the photon.
Okay, and then you're going to attach this.
Yeah.
So what is this diagram? Right. This is an electron coming, absorbing your photon, and then emitting. What else would you add to this? What other thing looks the same? Really? What is this?
Oh.
Right? Because you don't know the order of these. That's the only other. So there are those diagrams as well. What's the interpretation of this? I just gave it, right? This tells you about how an electron and a photon interact. What's that physics? What's that? Huh? No, but like Coulomb potential. When you have two electrons, well, actually, I haven't explained that yet. Okay. This is Coulomb physics, right? This is Coulomb physics. This is just a photon. Sorry, I misspoke. This is Coulomb physics. This two things, yeah, two electrons feeling each other's existence, right? And then this is, well, we're gonna discuss that. But it's basically an electron absorbing a photon and then emitting, or the order that is not sensible, right? Incoming electron, photon, incoming. How about this? What can I draw here? Tell me what to draw.
There's a plus sign because photons are boson and
Because both the incoming and outgoing states are distinguishable. Right? You could distinguish which is which. All right, what do I draw here? So tell me. All right, what are we gonna do here? Fermion. Okay, so I have to draw this. Then what? We're gonna go from there. Sorry, this goes where?
One goes here.
To this? That's
No,
not
to the
connected.
other one, fermion.
Sorry, this goes to fermion. What does that mean? Like this?
yes,
You connect.
yes, and we
Here, draw it.
I can try, I'm not sure. Yeah, this is the only thing which I can think of. It will be a box kind of thing.
Okay, so there's this diagram. This is kosher. What order is this?
Oh, 1, 2, 3, 4.
It's E4 and is one loop. So is there anything lower contributing to two photons scattering? No. The world would have been a weird place if photons were scattering off of each other. This is a very, very suppressed. It's essential. It's very, very suppressed. Okay, good. There's another diagram. Now there's a simpler one loop diagram that you've drawn. So there are, if you're discussing one loop, if I have a fermion coming in, what can I have? One loop.
It's like a sunset, a photon coming out and going.
What's this gonna do? This is gonna get added to what? It's gonna get added to the propagator. So it's gonna renormalize your propagator. It's a quantum correction to the photon propagator. And we're gonna see that what it does is shifts the mass. What other thing can I draw? Can I have a renormalization of the photon? Can I draw something here? Huh?
Oh, the electron position.
Yeah, could have a loop like this. Okay, so there is this one loop diagram. There is this one loop diagram. Is there another one loop diagram you could think of? Is there something you can think of that will change this? Is there one loop correction to this? So I'm going to erase this. Finish it for me. Is there connection to this?
Yes.
Okay. Oh, by the way, sorry, one thing. This is order E squared. This is order E squared. This is order E squared. E4, E2. So what is it here?
You turning that into fermion to the photon. No, to the photon.
Okay.
Oh, it is the same. It's like a triangle thing.
Okay, so triangle. So what do I draw in the middle?
The two.
All right, you guys will follow this. This is called vertex correction. We don't understand. It's called vertex correction. This is a normalization of the photon propagator, right? We're going to discuss this diagram, we're going to discuss this diagram, and we're going to discuss this diagram. This is called vacuum polarization. Actually, this is the easiest of all of them. So, of order E squared, the only diagrams we found are these three. So there, sorry, at order E squared, there are only two tree level things. Well, sorry, yeah, these two. We're going to discuss that today. Then for one loop, everything that exists as order E squared is this guy, and this guy. Three diagrams. Very likely we'll only have time to do one of them. Just one, which is a simpler one, called vacuum polarization. If there is time at the end of the semester, the course, we'll do these two as well. As sample calculation, one loop calculation. Good? All right, that was a long detour. All right, so let's start with the electron scattering. Here are the two diagrams. P, K. What is Q? Q is P minus P prime. What's Q prime here is P minus K prime. Good. So hopefully you can put the Legos together. This is the propagator in Feynman gauge. I'll be using Feynman gauge all over the place. So please work it out for yourself to see what the gauge is. Yeah, hopefully you recognize where these come from. So what's the origin of this gamma mu? There is this gamma mu, this gamma mu. What's the origin of these guys? The vertices. So the vertices will contract with the propagator, right? So that's what it is. That's how you get some engagement variant. Keep in mind that these are 4 matrices, right? So of course, yeah, you're going to end up with these 4 vectors, multiplications. And if you recall, when we squared them, we use these tricks of writing them as traces, right? Okay, so there's this. We did the Yukawa for that reason. And then there is this. Now, Pauli exclusion principle, I've explained this, tells you that there's a minus sign in between. Good? All right, this is electron scattering. The electron-photon scattering, the word I could not remember, is called Compton scattering. All right, so these are the two diagrams that we're going to describe. What we're going to do is we're going to take these two calculations, these two diagrams, add them up, and as a sample calculation, as I did before, I'm going to score them to tell you how it works. Just remind you how it works, right? Of course, you should expect similar identities. How many gamma matrices trace gamma? So each of these terms have two gamma matrices in them. When you calculate m star, you should have 4 of them. When you expand that, you're going to end up with terms with no gamma matrices, 1 gamma matrices, 2 gamma matrices, 3 and 4. Oh, right? The odd numbers drop out, so 0, 0, 2, and 4 use those identities. Good. This is the fermion propagator in the middle. Hopefully, you remember. That's right. This is a fermion propagator in the middle. Two-level calculations are pretty straightforward, but you absolutely have to do it because these are the trivial examples. These are the cases that you don't need to do any integrals. Integrals are when your life starts getting painful. Good. So we said that in calculating the amplitude, in calculating the cross section, what we wanted was m squared, right? This is a 2 to 2 scattering. Do you remember what the differential cross section was? The final form of differential cross section. We did this last time. We said there's some geometry associated with it. Well, go look it up, right? But basically, what mattered was m squared was in there. So here's what m squared is. It's order E4, right? Because the diagram is order E2. It's order E4. What is, oh. Yeah, okay, never mind. I have not introduced alpha yet. Okay. The external legs are on shell, right? So, which means that this k squared is m squared. There's only one m here, mass of fermion. Photon is massless, right? And then p squared is 0. Where is p? Oh, p. Because it's an incoming photon. The photon is on shell, right? So it has to be 0. P squared has to be 0. So it's p prime squared and k prime squared. So you know those relations. This allows you to simplify this expression. For instance, the fermion propagator here for q prime has this for wait, no, this one. I'm looking at this one. So this fermion propagator simplifies. This is what the actual form of it is. But if you expand it using the fact that the external legs are on shell, you could write it this way. It's a very, very useful trick. Every time one of your external legs is a photon, you should try to write the downstairs of this as the inner product. You will succeed. This is useful. Now, as we had said before, the spinner external legs carry spin. Sorry, fermion external legs carry spin degrees of freedom labels. So you might want to sum over them if you're not observing them in your detectors. And then the photon has helicities, right? The polarization. So you'll want to sum over them as well if you don't measure them. But how do you sum? You first square, then you sum, right? Because these are charges. Good. Now, there are ward identities. I already said, let me just discuss at high level. So let's say you have some sort of a scattering problem like this. This is the amplitude for a bunch of guys coming in and a bunch of guys going out. There is a photon, external photon. The photon is on shell. So here there will be some sort of an epsilon mu p star. But the fact is epsilon mu p star tells you that this contracted with p mu should vanish. Right? So whatever the contribution, whatever the contribution of m mu is, if you contract it with, where did I write this down? Yeah, if you contract it with p mu, it has to be 0. It's just an on-shell condition. These are called ward identities. But there are various ways to, it has many, many different consequences. Yeah, let me not discuss that in more detail, but what I want you guys to know is that yeah, that's basically it. Of course, if every time, think of at the moment, because the slide was written when I was planning on doing the full one loop, and you'll have to use the full power of it. But what you need to know for the purpose of now is that word identity is a statement that if you have some sort of scattering amplitude, a bunch of things coming in and a bunch of things going out, if there is a photon in your incoming or outgoing guys, you have to be on shell. So if you put for your incoming thing epsilon mu and your outgoing thing epsilon star mu, those epsilon mu's are functions of p, right? P is the momentum of the outgoing guy. That contracted with p should give you 0. So, well, the statement is, and this is a completely general statement, right? Doesn't matter what's in here. Doesn't matter what you're calculating. If, oops, if you have a p here, if this is epsilon star mu p, first thing is that this can be written as epsilon mu star p mu, I'm calling it m mu. Hopefully that's clear. And then this m mu better contracted with p mu gives 0. P mu is this mu. Just word. These are called word identities. The fact that the photon has 2 helicities total, 2 polarizations, right? Why are we doing this? Because we don't want to pick a basis, right? You don't want to pick a particular basis. It has to be orthogonal to the direction of P. You could pick P to be in the Z direction, right? Those guys, but that's ugly. You don't want to do that. This is nothing but the conservation of charge, current. And I encourage you to figure this out, why this statement is true. Well, it's just simply the statement that M mu is J mu evaluated in this matrix element. Can you see that actually? All right, I'll not push it. All right, any questions? Of course, this will not be the last time you hear Gore. These are all over the place. It's just gauge invariance and the fact that we write down in the propagator of the photon, we write down epsilon mu, epsilon star mu. Those guys have only 2 degrees of freedom. And those 2 degrees of freedom are in the direction perpendicular to the direction of propagation. So if you take m mu, if one of your external legs is the photon, if you contract it with p mu, your m mu has 0. What are the epsilons? Polarization vectors, right? These are the final rules for QED. Questions? How am I doing on time? It's all right. Yeah, so here I guess I was planning on saying more. Okay, so here is I guess a homework problem for you guys. So after all, maybe there is a homework for this part of the course. So what do? You take these 2 diagrams. When you square it, you're gonna get MA squared, MB squared, and then MB star MA plus Hermitian conjugate, right? So let's focus on MA square first. Let's just focus on that term. If you do that calculation, after, by the way, you use these simplifications that I suggested you use. You see downstairs, you end up with P dot Ks. So Once you do those calculations, in this particular case, after some Dirac algebra, you find the following expression. This P dot K squared should not surprise you, right? It's just basically the term that you expected. You end up with these expressions. Okay, can you see where these come from? The M4 term, where does it come from? In the Yukawa theory, we saw the exact same term, right? Every time you have a fermion, you had 4 gamma mu's potentially. Every time you have a gamma mu, it's gamma mu plus an M. So when you expand it, there's a term that has no gamma mu's, and it actually has 4 M's. That's M4. Those are those terms, right? Then the counting of the degrees of freedom, the number of M's will tell you how many gamma mu's you've contracted, right? So this is the term that had 4 gamma mu's. These are the terms that had 2 gamma mu's, right? So this way, even though you haven't done the calculation, at least term by term, you see where they come from, right? Let me copy paste this, which was the, we're squaring this one. So let me draw it here. Where am I? Yeah. I already forgot. This was P and this was K. This is K prime, P prime. Let me check. Yeah, KP, K prime. No. Yeah, the other one, the other way around. K, P, K prime, P prime. All right. What does this look like? This is K dot P. This is K prime dot P prime. This is K prime dot P, right? This is K dot P. This is K dot K prime, and then there's an M squared term. And P dot K is here, 2P dot K, right? So staring, if you did a lot of these calculations, you would stare at these, and then you come up with some nice variables called Mandelstam variables. S is P plus K. What is S? What is S? It's just this guy squared, right? I call this Q or whatever I called it, right? This squared is S. What's the interpretation of this? What's the interpretation of S? This is the Mandelstam S variable, and there are various ways to write it down. What's the interpretation of it? Center of mass, energy, squared. Center of mass, energy squared. So all of these guys, first by dimensional analysis, you see they have the energy squared. Or length minus 2 order. The T is K prime minus K squared. Okay. And then this is P prime minus K. Can you see where this P prime minus K is relevant? If you had the other diagram, right, then this would be relevant. So when you compare these 2 diagrams, it's like S and U are flipped. Well, the U plays the role of S in that one. There, now I encourage you to think about T, how T is related. Can you see it? All right, think about it. Now, an interesting exercise for you is that S plus T plus U is 2M squared. So if you cannot interpret what T is, just think of it as 2M squared minus S minus U. These are not independent. They're only 2 independent variables. Good. So the amplitude squared, in this case, you could write it as a function of two variables. And you pick whichever ones are that are can be in S or S and T, S and U, T and U, because they're not independent. Why is it two variables? These are two real variables. Does it match the counting we did before? How many free parameters are there in the scattering problem? Well, there are, if you remember when we did the counting, there were 6, right? And the 4 conservation laws, we subtracted them, we ended up with 2. So we expect 2 real variables. Okay, so here's MA squared written in terms of S and U. Why S and U? I just explained to you why it's easy to write in S and U. If you do the MB calculation, so here is the MB calculation. Let me see. It basically, you get the same answer if you send P to minus P prime. I just said that MB result can be found by swapping S and U. So you don't need to do the calculation again. This is the advantage of thinking in terms of Mandelstam variables, right? You just draw the diagram and say, oh, this diagram goes to that diagram. If I label things, swapping P and minus P prime. That, for me, what it would do is that it would swap S and U. So we did the calculation once and then swap S and U. You get the answer for MB squared. Here's the answer for MB squared. Now, MA star MB, now you have to do the calculation. This is the answer you find, and you have to average over initial spins. You get 1/4. We did this, right? And all right, so you put all of this together. Quarter of sum over MA squared is now 2E4. Why E4? Because every amplitude had E squared. Now we're squaring that is E4, right? The sum of these terms. There are 4 terms, right? Where are they coming from? Well, you had MA plus MB, the whole thing times this star. So there are 4 terms. Good. So this is the full answer. It's written covariantly. Everything is nice. But if you want to relate this to the lab frame, you could pick your initial. In the lab frame, you could take K mu to be, well, K mu was what? K mu was a electron, right? You could take the electron to be at rest. Here is electron being at rest. The photon is coming in with some initial momentum, and of course, you take it to be in the z direction, for example, right? That energy, this is just on shellness of it, right? And then the outgoing fermion, you could write it this way. You know, like I've explained these things many times before, right? So you have the conservation of the jet momentum, and then this is your answer. This is your final answer. What did we calculate? We calculated something here. We calculated this square. Right? So this is the content of the electron-electron scatter. Sorry, no, electron-photon, Compton scatter. Electron, I just wrote the 2 diagrams, I did not square them. Electron is very similar to the Yukawa calculation that we squared. Now, what if you have a theory where you have a photon, a couple of different fermions coupled to it, right? Now you could have diagrams that look like this. This is electron. This is positron, fermion, antifermion, annihilating to say another electron, another fermion is muon and is antiparticle. The comment I want to make here is that you stare at this and you realize that you could recycle your old calculations. even when you have a theory with a couple of different fermions, it's the structure of the diagram that dictates everything. So that's why these Mandelstam variables are so smart. But this is something that it takes some you have to convince yourself that these things work. But just like it's helpful to stare at it, right? Like, so here, what is the this is the vertex. Same thing here. If the charge of the muon is the same as electron, which is the case, right? So here's the same diagram. The photon propagator is the same. The only thing that's changed, what has changed? It's a fermion. The only thing that changed is that this outgoing legs have different mass. It's the only thing that's changed. But did that matter actually in your calculation? The external legs, right? It really didn't matter. Well, it matters in like when you take it to the lab frame and do the calculation over it. In the final cross section, it matters, but in the calculation of the M, you're oblivious of how it works, right? All right, good. I'm gonna pause here. I went a little bit too fast, but questions? Okay, good. All right, so QED. What are the lowest order E squared two-level diagrams I can write? There is this. I'm not going to put the arrows because we have the other processes as well. Are these? Then, oh, thank you. Then there is, oops, sorry. There is this. Right? Is there something else? Nothing. These are all you've got. When you go to one loop at order E squared, this is the correction to the propagator of the fermion. So this is the diagram, this is order E squared, we're going to consider. There is this, which is a correction to the propagator of the photon back in polarization. There is one more thing, a correction to the vertex. You didn't finish that, so how do I draw this? Let me do it for you. This is all you've got. But that is EQ. It's not E squared, that's right. There's no E4 here. All right. These are classical answers, and these are one loop quantum corrections. When you write down an expression for the propagator, we're going to see that the effect of this is going to be that adding the two to the first order, you could view the correction as the same old propagator, but with a new mass. We already had some hints of that. That's called renormalization of the mass, because your quantum corrections have shifted. Where did we see this? Do you remember? So in the 5-4 theory, we had a renormalization. This was this renormalized the mass of the 5,4 boson by an infinite amount. And I said I will come back to it. But here is a similar thing. This is going to renormalize the mass of the fermion. How are you going to interpret this guy? Can this renormalize the what is the mass of the photon? 0. Can it give it a mass? Photon cannot have a mass larger than 1 + 1 dimension. That would violate gauge effects. You can miss yourself. So what happens here? You know? So let me give an example here. So in this setup, what was the property? It was p squared plus m squared plus I epsilon. So one thing that can happen is that the mass can get renormalized. What else can happen? The whole thing could be multiplied by some large one. What this is called the wave function renormalization. Because you could think of this is a 2-point function. You could think of this as being, you could keep this in your field, fundamental field 5. So there is a wave function renormalization, potentially, and then there is a mass renormalization, right? So here, this, we'll see, we'll discuss this, right? And then there's a vertex renormalization. What does this renormalize? Coupling, charge. I'll leave it to you guys to figure out how it works. All right. So what does it seem like happening? It seems like we start with the theory. You put in a bunch of variables in your Lagrangian. As you start doing quantum corrections, you realize that those variables you put in the Lagrangian are not necessarily the variables that are going to decide your observations. Because the loops are going to shift those values. This is the phenomenon of renormalization.
What's the third case of renormalization?
Charge. Well, what is this diagram? Third case, this one, right? Yeah. What is this diagram? Think of this. What does it tell you? It tells you how strongly a fermion interacts with the photon. What is that concept? Charge, right? Because what was the diagram? This was correction to. It was a correction to this, which was minus IE gamma mu. Right? Renormalization of charge. Good. All right. So let me talk a little bit about. So what we're gonna do is we're gonna pick the simplest of these diagrams is vacuum polarization. This guy. So let's pick this dude and talk about this. Good. I'm going to talk about it a little bit today, and then next time around, we're going to calculate it. You should expect infinities in here, right? The same way that we saw infinities here. So there are two ways to interpret this. One way is that it's a contribution to the 2-point function of the photon. Or you could view this as a contribution to the S matrix, a photon turning into another photon. All right, what is this Feynman diagram? It's half because of the symmetry of swapping these two. IE squared, where does the I squared come from? 2 vertices. There's the gamma mu, those are the 2 vertices. Each vertex has psi bar, psi bar at points x and y. This is V interaction, V interaction. This is in position space because I wrote it as a contribution to the 2-point function, position space. Good. So here's something I've not explained. Yeah, I've not explained this. I think, will I explain this? Yeah. there's an important thing. So far you have not seen, this is the very first time you see a fermion loop. A fermion loop always carries a minus sign. A boson running in the loop has no sign, extra signs. A fermion running in a loop has a minus. Do I need to justify it or derive that? Derive that. You know everything to derive that. All right. So what is this? This is a 4-point function. This psi bar psi are at y, and then this psi and psi are here, right? Now you just expand the whole thing. You realize that your A mu has epsilons. These are the polarization vectors, right? This guy is the star, this guy is mu. You already noticed that I was drawing my Feynman diagram going up. Now I'm drawing this way. It doesn't matter. I'm writing explicitly that gamma matrices are 4x4 matrices. So I'm keeping track of the label, right? These fermions, I'm viewing them as Dirac fermions. So I'm writing the component. I'm integrating over x and y. Hopefully you remember y. WHY, yeah. But what is the interpretation of this term? This is a 4-point fermion diagram, right? So what is time ordered, by the way? So the time ordered thing is basically two of these guys, right? So it looks like I don't want to draw it. Oh, well, actually, no, let me not draw it this way. So first of all, I'm writing the labels very, very explicitly, right? So there is this term, and then there is this term. But because I put the psi bars to the right of psi's, these are 4x4 matrices. Good. Remember that psi's are 4 vectors, the other guys are rows. When you calculate the amplitude, it squares with this. Hopefully this expression is very familiar, right? So because I put them like that, you end up with a trace, right? The epsilon mu come out, and then there's an integral over dx dy minus e squared. Good. The sign is very important. It's minus. All right. Why am I going over this? I'm not planning on doing this integral now, this calculation now, or physically interpreting it. But I want you to stare at it and think about the consequences of this variable. And
Sorry, like initial photon and the final photon. 1 and 2. 1 is
The vector state vectors. State and he's talking about state and class.
these. Yeah, it's what did I mean here? Yeah, initial and final photon. Yeah. Yeah, yes. Yeah. Thank you. All right. I just want to have a comment about go on a tangent. Because for the first time ever, I finished early, but I will have a point here to describe. How many of you guys have heard of supersymmetry? You've heard. So yeah, that's okay. That's fine. All right. You're familiar with well, you're probably the most comfortable thing for you guys is scalar field calculation. You have a scalar field in nature. Higgs. So there is a scalar field in nature. All right. Let's go it this way. This is a propagator for the scalar field. What is a propagator for scalar field? What's the Higgs propagator? Just say it. 5 over P squared plus M Higgs squared plus I epsilon. Right? Good. What would be the first quantum correction to this? Well, if Higgs couples to fermions, they're going to have terms like this. Fermions running in the loop, right? All right, so you have these things. You could also have, if Higgs couples to fermions, actually, how do I want to say this? Yeah, one way of saying it is this. So there's a fermion running in the loop, right? And if there are bosons, they could run in the loop as well, right? So let's say you have some bosons, they run in the loop. I don't have to draw. One of the issues that we have in standard model of particle physics is that it's hard to protect masses from quantum corrections. Particles can run in the loop, right? And whatever masses you put in the UV, the masses are going to grow larger and larger, right? We'll see that for cases like photon, the mass is protected. It won't be increased. Masses remain zero. It has to, right? It's only wave function optimization. But the issue is that these guys can run in the loops and they contribute a large amount. And we say, okay, how large of an amount is it? Well, you have to cut off these intervals. And the natural thing to put, you say that, oh, I'm going to cut it off at L Planck, very, very large energy scales. That means that your masses are going to end up picking up corrections that are enormous. You have no phenomenological reason to explain why the mass of Higgs or some other particles are small. Masses become large. One old idea was that, well, there are bosons that run in the loop. There are fermions that run in the loop. So we just learned something. Fermions come with a minus sign. So if for every boson, there's exactly a fermion with the right charges, when you add up the contribution of loops, they cancel out perfectly, so your masses are protected. This was one of the motivations for supersymmetry. So, well, there are many motivations for it, but one way of motivating is that there's some sort of a symmetry of nature that guarantees for some reason, supersymmetry does that for you, that every particle that comes with some mass, the same way that now your fermions come with antifermions, every particle comes with an antiparticle. Here, and that's a consequence of Lorentz symmetry. Here, if you have a larger symmetry called supersymmetry, for every boson with set of charges, there is a part in a fermion. When they run in the loop, they cancel. This is one of the main motivations of supersymmetry. Okay, so that's all I wanted to say. Do derive why there's a minus sign associated with fermions. That's the whole point of this discussion. All right, any questions? We talked about this, I think we talked about this last time, right? In 52, we discussed this. Yeah. This has a name. Does anyone know what this issue is? It's called the hierarchy problem. The hierarchy problem is this. It says that why are the masses of particles in the standard model so much smaller than in Planck? Because the loops will just blow them up, make them very large. Now there are particles that the mass could not be corrected, like gauge charges, but scalar like Higgs, there's no symmetry that protects it, so you shouldn't expect something like that. Anyway, enough for orthogonal directions. Any last questions? For what? Oh, I didn't say it fails.